Our webinar today is on using Coreform Cubit and the Open Fusion Toolkit for fusion energy applications. We're pleased to have Dr. Chris Hansen joining us from Columbia University to walk us through how he has been using Coreform Cubit with his code Open Fusion Toolkit. We're going to walk through today in terms of features of Cubit is model creation. He'll be showing some model cleanup using the imprint and merge feature. He'll also be showing us how to use quality metrics feature to identify bad elements and fix them. He'll walk through using block assignments to define regions in your model and show us how he interfaces with the third-party solver via Python scripting with Coreform Cubit. With that, I'm going to turn it over to you, Chris.
So yeah, as Kimberly mentioned, I'm going to talk about how we use Coreform Cubit along with our suite of codes, which is called the Open Fusion Toolkit, to do various studies within fusion energy applications. All right, so here's the outline. So I'm just going to give a brief motivation at the start here, talk a little bit about status of the fusion energy industry, why we need tools like Cubit, then summary of the codes, and then I'm going to go through a couple examples of using Cubit for 3D magnetohydrodynamic simulations. So these are fluid simulations that are coupled to electromagnetics, where the fluid is a plasma. And I'll have a couple cases there, and then talk about how we use it also for doing thin wall electromagnetic simulations in 3D, where instead of volumes, we're treating surfaces with the boundary finite element method. Okay, so yeah, you may have heard a lot about relatively large amount, right, compared to previous years about fusion in the news recently. So here's sort of a sampling of these things over popular press. So there's been a lot of interest in this, some sort of scientific achievements from several devices in terms of reaching threshold milestones. And so there's been, a lot more interest going forward. But more than just even the popular interest, there really is sort of a global consensus that has developed now within the scientific communities that fusion is finally, after a very long gestation period, ready to kind of make these steps to commercialization and try and push that pathway forward. So this consensus exists both in scientific and industrial communities. So there was a 2019 National Academies of Sciences report in the United States that endorsed this idea of kind of readiness to do demonstration facilities and develop commercialization efforts. And then that was continued within US policy through the White House and the US Department of Energy through the development of milestone-based development programs targeting commercial fusion development. But we're not, of course, the only country doing this. Many other countries are pushing forward at the same time. So the UK has similar programs, and the EU and China and other countries and groups have similar sort of development efforts. And actually, I think most interestingly, beyond government programs, which is where most of this development has happened so far, there's now a huge private industry that's developing. So there's more than 4 billion. I think that's kind of an outdated number, maybe approaching like $6 billion total in private funding that's already been dedicated to fusion startups. And so now, in addition, I'm showing a few examples of kind of the pathways that are being pursued. So there was a large multinational research endeavor, the ITER project, which is being built in the south of France. And then here's two private efforts that have popped up just in the last decade and have actually, in that decade have already surpassed essentially the state of this public development that was happening from earlier on. So here's a couple examples: Commonwealth Fusion Systems that was spun out of MIT, and Zap Energy that was spun out of the University of Washington in Seattle. And you can see there's quite a difference here in scales, right? This is a very large facility. You can't even see people down here. This is somewhat mid-scale, and this is something on the size of an individual person. And all these are sort of trying to target, in some sense, similar parameter regime. So there's quite a breadth of approaches being pursued. And the reason why, of course, there's this interest in pushing this forward beyond the scientific readiness is that, we want to use this as a resource to allow us to get to a fully zero carbon grid, and crucially get us those last, portions of the grid removing carbon that really require sort of the ability to have on-demand power production, which is currently a largely sort of unfilled gap in terms of a cost-effective resource there. So I have a few sort of examples here I just want to point out. So what I'm talking about here, this is from a paper in Joule in 2018. So basically this, each half of this plot is the same graph. And what it's showing is the cost of electricity as you move from high CO2 intensity in your grid to low CO2 intensity from left to right. And the two cases here are essentially like intermittent resources like renewables and storage on the left, and then intermittent renewables, storage, and some sort of, on-demand carbon-free power generation that's more expensive than those resources, but still at some modest cost on the right. And you can see, as you get to very low CO2 intensity, the cost goes up dramatically if you're relying on intermittent resources and storage, as opposed to having some firm source of energy. And the primary region for this is, particularly in regions away from the equator, right? You have huge seasonal variation in the intermittent resources, and so you have to start, significantly overbuilding or dramatically increasing your storage capacity to handle that seasonal variation. So if you can capture that with some sort of on-demand resource, it's very desirable. And there's another sort of element to this, which is that having a resource like this can also support continued growth in energy usage without emissions. And this is really important for equitable energy access globally. So if you look at all these projections, and here's an example of this from the IEA, of projecting forward, how we're going to get to net zero. And you can see that, of course, we're increasing renewable capacity, we're dropping down fossil fuel usage. But if you also notice that, this is a totally different paradigm. We've gone from, in all of history, we've been increasing energy usage in time. And this going forward is saying, not only are we going to stay basically flat, but we're going to decrease energy usage. And this is a challenge, right, as you have development in the rest of the world. So what we'd really like to see is this to be able to continue to grow for equitable access to energy, which strongly relates to, quality of life. But of course, we'd like to do that in a way that doesn't increase CO2 emissions. So having a zero carbon source like fusion would be very, very desirable. All right, so the leading approach to commercial fusion energy at this point is so-called magnetic confinement. So to make fusion happen, we have to reach conditions like those that happen in the core of the sun. So obviously we need to isolate our fuel away from material surfaces in order to do that. And the way we do this with magnetic confinement is we utilize the fact that fusion fuels in the form of a plasma, superheated gas, and plasmas are forced to essentially follow magnetic field lines. So we can see this if we look at a picture like this at the surface of the sun, and you see these solar prominences that come off. And this is plasma from the surface of the sun that's flowing up and forming this arc structure. And the reason why it fills this arc structure is because there's magnetic field that forms that same structure, and the plasma is essentially confined to follow that magnetic field. So you can see it makes these very thin spaghetti-like structures, and it can fill in across the magnetic field, but not perpendicular to it. So if we imagine taking one of those arches off, connecting the ends and forming a donut, we can then use this structure to fully isolate fuel from the walls, and then we can heat the plasma. So this is schematically kind of what this looks like in devices on Earth. This particular configuration with sets of magnets here is called a tokamak, where you have your toroidal plasma here and several sets of magnets producing that confining magnetic field. Here is what an example device looks like. This is the JET tokamak in the UK. It's currently the largest operating device, and then overlaid is a plasma discharge here. And this works extremely well, and we can reach temperature gradients in excess of 1 billion degrees Kelvin per meter. And that's what allows us to reach conditions similar to the core of the sun, in practical spaces on Earth. And this works quite well. So you might have, one of the news releases was from the last year. And in fact, they updated this very recently. The JET tokamak did experiments with fusion fuel in the last year and demonstrated record energy production. Again, this is an experimental facility. It's not a commercial development facility, but it still is showing, that this process works, and within our experimental capabilities now can produce large amounts of energy. So this is a pulse device, only runs for a few seconds at a time, but you can see here during this 6-second period, they produce continuously about 12 plus megawatts of fusion energy. So a significant amount of energy from fusion in these devices and in a fairly stable way throughout the discharge. So this is sort of what provides the confidence that now we got to push forward and develop this as a real energy source. But this now creates a need for really kind of new tools. So the transition from research endeavor to commercial endeavor really needs new engineering focused tools. So for engineering systems, we really want predictive models. Numerical analysis has been revolutionary in a lot of design fields like aerospace and other things in reducing the cost and accelerating the design cycle. And this is particularly important for cases like fusion and aerospace, where there's a pretty high cost of prototypes. But effective use of these tools really requires tight integration with the design analysis cycle, right? So we want to be able to say, here's the design we have, how does this work? And then we want to be able to adjust the design and reperform that analysis. So this involves, you want to be able to interface with CAD and have relatively fast turnaround. So our existing research base really provides a solid base for this, but the needs of commercial design really require us to have new tools. Okay, so I'll talk about now a suite of tools we're using to basically look at this problem of bridging from research level tools to engineering level tools. So this is the Open Fusion Toolkit, which is primarily developed by myself and other members at Columbia University in the Plasma Physics Lab, but it's a growing community. It's an open source toolkit that has a suite of both 2D and 3D tools for applications in plasma and fusion science engineering. Code is freely available on GitHub, and there's binary builds as well as instructions on how to build it. So all the tools share a common code base and apply finite element approaches on unstructured grids for geometric flexibility to allow us to integrate well with CAD. And the underlying toolkit provides all the functionality you need to basically then just work on the physics problems at the top level. The toolkit uses a combination of Python, Fortran, and C and C++ to give usability while also retaining performance and scalability. So this allows us to address problems, that you can run on your laptop in a Jupyter notebook, and then all the way up to very large HPC environments. Okay, so I'm going to talk about a couple of the tools that I'm going to discuss generating meshes for here. I'm just going to go over these really quickly. There's publications I reference here if you have more interest. So one of the tools we have is a 3D thin wall eddy current modeling tool. So this is called Thinker. So in these magnetic confinement systems, you have a magnetized plasma and large magnetic fields produced by these coils. And in general, there is always some startup process or other, periods during the discharge where you're going to have time dependence of these fields. You're going to have varying fields. And so this is going to drive currents in surrounding conducting structures and produce other fields and things like this. So it's important to be able to understand the interaction between the actively controlled magnetic field coils, the plasma, which has some natural dynamics to it, and then the passive conducting structures that, form the rest of the device. And so here's an example, of something like this, where we want to look at a structure like this, and we want to see, what sort of currents are going to be induced in these surrounding structures. And we can do this in a thin wall limit, in this case, where we use a boundary finite element representation. So all we need to model is the surfaces themselves. We're not modeling actually the full volume of the system. So this is a very flexible approach. It allows us to look at lots of complicated systems. Primarily, we look at these again for the structural components of the vessel, which you'll see when I go forward, but various cases where you have large induced currents, and these can be fairly 3D currents as they move around various structural components. The other case I'm going to talk about here is our code. It's called MUG. It's a magnetohydrodynamics on unstructured grids. So magnetohydrodynamics is a plasma model where the plasma is treated as a fluid, and it interacts, of course, with Maxwell's equations. So this is a fairly unique code in the space, in that it's a nonlinear MHD code that's capable of modeling arbitrary 3D plasma regions. So we do this through unstructured tetrahedral or hexahedral representations, but we can still get very high geometric accuracy, even with relatively coarse grids, by using higher polynomial order finite elements, and we can use curved elements to capture the geometric representations there as well, which Cubit is very helpful for producing this. And this has been applied to complex 3D plasmas and is continuing to be applied to these cases. And I'll talk about a couple here. So this is just to give you a flavor of what an MHD model looks like. it's a lot up here, but basically, you have the Navier-Stokes equations, where you can also have multi-species energy equation, basically, because the electrons and ions can oftentimes behave with different temperatures. And then all this is coupled to Maxwell's equations here, given by this generalized Ohm's law and some relatively complex transport. You often have highly anisotropic transport relative to the magnetic field direction, as I mentioned. And similarly, this is a highly flexible tool, which allows us to basically take any given plasma representation, mesh it up, and run simulations on it. So Cubit is the primary meshing tool we use for Open Fusion Toolkit. And this allows us to get high geometric fidelity. So it provides both the power to mesh geometries with minimal defeaturing, which limits, sort of the complication of interaction with CAD and engineering terms. Oftentimes, we get like a whole CAD model like this, but of course, we're only interested in some select features. So it allows us to defeature and build the mesh we need. It also provides us the flexibility to pass additional mesh-based information. And this is particularly important as we're doing exploration of these tools. So for example, certain models like the thin wall model requires us to define locations of jumps in multi-value potentials and other sort of composite elements that need to be defined based on topological information from the mesh. And so Cubit allows us to define this information in a GUI setting and then pass that through. So here's an example, where we're defining topological loops that can be passed into the solvers. And actually very important for us is also the availability of a sort of a multi-context licensing system. So we can use Coreform Cubit for our commercial projects, where we're working with industrial customers and on industrial funded research. But we can also then use Sandia Cubit for all of our DOE funded projects, because DOE is still a large funder of fusion energy. And so this allows us to use a common cohesive tool, but with a licensing framework that's appropriate for each of the different research contexts we work on. And as Kimberly mentioned, the way that we interface is primarily through essentially like Python intermediary scripts. So what we generally do is we output Exodus files from Cubit. So this is a really flexible mesh format. If you haven't used it before, and again, you need this ability to kind of define a lot of different types of geometric information that might not fit into the normal CFD or FEA boundary condition or material workflows. Definitely look at Exodus. It's really flexible. And then what we do on our end is, and this is essentially just a convenience thing, we do some additional pre-processing with Python scripts. So basically we take the Exodus 2 files and we map them to a native format within the code, which is actually very similar to Exodus 2, but the Python script, one, allows us to convert from netcdf to HDF5, so we don't have to link with netcdf, but also allows us to do some basically reorganization. So we can do that in Python in a really convenient scripting format, and then have a well standardized format for a given tool, say Thinker, that can be read, really efficiently in compiled code, so in the C and Fortran. And this also allows us to map additional tools through the same infrastructure. So, in some cases, people might want to use a different code like Gmesh, or for, really simple 2D cases, the triangle code. And these are, other ways to do it. But, again, this is all sort of modeled off after the Cubit Exodus workflow, because this is just such a good flexible environment. So yeah, I encourage people to look at this. It's very easy to interact with the Exodus files in Python, and do any, like I say, rearrangement or tweaking that you need to do, so you can take that effort off of compiled code. All right, so now I'm going to talk about a couple of Cubit applications and kind of walk through actually generating the meshes. So the first one is building a unstructured tetrahedral mesh for 3D nonlinear MHD. So this is a very complicated geometry, so it'll be easier when you actually see it in 3D as I can move around the object. But essentially we have this very complicated structure. Here's a CAD model of it. Here's what it actually looked like in real case. And there's essentially this main volume down here, and then this complex sort of toroidal structure up here, and that is connected at 4 points to the main volume. And so this complex combination of these two is the plasma we're going to try and model. All right, so let me hop over here to Cubit. All right, so hopefully everyone can see my Cubit window here. So one thing I'll just mention, so I generally, the way that I work is I like to build up journal files as I do any sort of mesh work. So a lot of times I'll do things in the GUI, but I want to save out the commands to a journal file. And this is so I have something repeatable, so I can get back to the state I was if I make a mistake or something like that. Sometimes, undoing in these complicated models is just not so efficient. So I'm going to do a combination in these examples of the GUI, and then also just kind of executing some journal commands, which I will try and show. But yeah, so we'll start here by just importing the mesh. So it's this ACES file. And in this case, we don't need to heal. And we're going to go ahead and turn off convert free surfaces to boundaries also. And then we'll just go ahead and import. Okay, so now you can see this is basically what we got from our engineering team. So this is that interior volume. So now hopefully people can see what the structure looks like. There's this toroidal region that's then connected to the main volume. If we look at the main volume is actually topologically spherical, but just barely. So it's actually kind of like this bow tie cross section, which is then revolved around. So there is a space here in the middle, so it's still topologically a sphere, but almost a toroidal structure. Okay. And so we're going to do like a little bit of manipulation here. So first, as is often the case, we're going to go ahead and scale this because we were given things in centimeters, and we want to run everything in the code as meters. So we're just going to go ahead and do a uniform scaling here to scale it down to centimeters. And then, of course, it goes tiny, so we got to resize that window. Okay, so the next thing we're going to do is, as I mentioned, a lot of times we want to define additional features. And in this model, in order to drive the boundary conditions for the magnetic field, which are applied up on this upper structure that we call the manifold, we're going to need to put in some cuts so that we can apply locations for jumps in multi-value potentials. And so it's beneficial for us in this case to basically isolate the manifold from the rest of the mesh so that those cuts don't go down into the rest of the mesh. So I'm going to go ahead and do that by doing a web cut. So I'm just going to go ahead and make a rectangular surface here. Just doesn't matter what the size is in this particular case because I'm just going to be using it to do a cut later on. Okay, and then I'm going to go ahead and move this surface up. And what I want to do is I want to surface, and I want to move this surface, and basically I want to separate the upper part of the manifold from the lower part. So I can do that by just cutting it basically right at this curve. So I'm going to move this up to an entity, and I'm going to just select that curve and go ahead and hit apply. And then what I can do is go ahead and web cut the volume. Surface. Okay, and then we go ahead and select that surface, apply, and then we can go ahead and just delete this surface since we don't need it anymore. And now you can see we've isolated this top manifold structure from the rest of the volume. Okay, so now it turns out that there's some issues here with this CAD around the interface of the main volume up to the manifold. Now, this is kind of bespoke to this particular thing, so I'm not going to go through the particular way of how I fix it, but basically I'm just going to run some commands here to go ahead and clean up this volume. So you'll see some stuff flash by. All right. And now what I want to do is I want to create these cuts in the geometry so that I have corresponding surfaces in the mesh where I can place my multi-value potential jumps. And so what I need to do is basically create a cut in between each of these connections between the main volume and the manifold. So it turns out that the orientation of this machine, you could basically create the surfaces, rotate them 45 degrees, but in my case, I'm actually just going to go ahead and rotate the entire volume. So I'm going to go ahead and rotate the whole volume to a slightly easier orientation. So I'm going to rotate it 45 degrees along the z-axis. And then what I'm going to go ahead and do is web cut this with coordinate planes. And so now you can see this is aligned with the X and Y axis. So I can just go ahead and cut this volume with first the YZ plane, and then cut both the corresponding volumes now with the XZ plane. Okay, and so now you can see I have nice clean cuts here, which will create surfaces in the grid, which I can go ahead and use to define those multi-value potential jumps. And now the last thing I need to do is I just need to go ahead and rotate everything back to its initial orientation. So I'll just go back minus 45 degrees. And there we go. All right, so now I have to do, these are all independent volumes at this point. So I have to imprint all the features so that they will be synced together. So I'm going to go ahead and do an imprint on all the volumes. And then I'm going to go ahead and similarly do a merge on all the volumes. Okay, so now we should be ready to go to mesh this structure. Okay, so first I'm going to start with just doing a surface mesh. Oftentimes I find for complicated structures like this, where I want to do an unstructured grid, oftentimes it's very useful to just mesh the surface first and then mesh the volume afterward. A lot of the problems usually are at the surface, so usually you can kind of pick out the problems here. So I'll go ahead, go over to my surface mesh settings. I'm just going to use a approximate size setting here, and I'm going to target a relatively coarse, wrong window here for all the surfaces. I'm going to go ahead and use about 3 centimeters. So you see, this is modestly fine, but not crazy. So I'll go ahead and apply that. And then I'm going to go ahead, go over and set my mesh type. I just want to make a tri-mesh on all my surfaces. And I'm going to turn off geometry sizing because, I don't necessarily want to, I want to kind of enforce coarseness and not worry about if I'm capturing exactly the curved surfaces at this point. Okay, so I'll click apply scheme and then mesh. And you'll notice it's gonna yell at me here. It's gonna say this model contains overlapping surfaces. It actually doesn't contain overlapping surfaces, but you'll see why it thinks there's overlapping surfaces in a second. So I'll just go ahead and say continue meshing. Okay, so go ahead and do this. Get my display. There we go. All right. Okay, so, well, this seems like a reasonable surface mesh, but it turns out there's actually some problems in here. So I'm going to go ahead and look at the quality metrics on this surface mesh, look at the shape metric, and just go ahead and apply and see what it looks like. And, these metrics, as many of them are, 1 is good, 0 is bad. And you can see the scale goes all the way to 0, which is not good. That means there's some really bad elements somewhere in here. And it turns out they're right in these little sliver you can see leading in. So there's this surface here, right? And this surface is coming into effectively like an infinitely small region there at the edge. It actually goes all the way to the edge. So this gets basically like almost infinitely tiny. So it's making just extremely poor elements in that corner. And there's a few other spots, but you can see these are really bad. And this is actually why it thinks there's overlapping surfaces, because effectively this surface is going to 0 thickness here. And so it thinks there's some overlap up here within sort of the tolerance of those measures. We can also refine this a little better if we filter the element quality range to just show everything below 0.2. We can go ahead and do this. You'll notice it keeps the curves that they're connected to. So sometimes it can be a little tricky to see, but if you zoom in, you can see again, okay, here is the problem elements, right, are in this slit. You can see there's a few other locations on the mesh where there's some problem elements. They're not so bad. A lot of these are up near 0.2. They're not down at 0. But this sort of view allows you to zoom in and figure out where problem cases are in your model. Okay, so I'm going to go ahead and do some tweaks now to fix this. So as I mentioned, I often use journals. So you'll see I'm now just going to replay basically everything up to the imprint and merge in my journal file. So it's just going to run through all those steps I did before, but much more quickly. All right, so here we are right before basically I did the meshing. So the problem is with these little surfaces here that come into this sharp corner. So the way I'm going to resolve this is I'm going to do this by compositing those surfaces onto the adjacent surface. And what this allows is for elements to go across this region. So normally, all your curves are going to be meshed first, and triangles can't go from one surface to another surface. But by compositing, it creates a virtual surface across the whole region, which allows basically triangles to go across. And so you're going to miss some of the geometric fidelity there, depending on your resolution. But you're also going to get rid of this really sharp region. So we're going to go ahead and do that here. You go to this construct virtual geometry, you go to surfaces, we go to composite, and we're creating a composite surface. And then we just select the two surfaces we want to composite. We hit apply. We look at this now, you'll see this line has turned into a dashed line. That indicates, right, that these two surfaces are composited, and this line will not be meshed. It will not be enforced to have, be meshed as part of the initial curve structure. So I can do the same thing, for this adjacent one. And of course, I'm not going to do the whole thing all the way around to save time. So I'm going to go ahead and just, again, off screen here, rerun this with the steps to generate composites for all those small surfaces there, and also throughout some other regions of the mesh. Okay, so now you can see I've taken, these ones. I've also defined some other composite surfaces down here to remove some of the small features. So now I'm going to go ahead and run through the same stuff. I'll just generate, again, off screen. I'm just going to run the commands I had before, generate the mesh, and now regenerate the quality metrics. And so you can see now all these regions up here are perfectly good. So we still have a few bad elements. And if we look zoomed in at those, we can see there's, now, okay, there's far fewer of these, but there's still a few of these that, we could go in further and clean up. Okay, but we'll go ahead and just go ahead and move through and say, well, what's the volume gonna look like? So we'll go ahead and now generate the volume mesh. I'm not gonna go through this in the GUI just because it's very similar to the surface mesh. So we're going to make a tetrahedral volume mesh. I just did this through the journal file. And then I'm going to do the same thing here now with the volume to look at the quality metrics on all the volumes. And we'll see, okay, so we have, pretty good up in these problematic structures before, but we have some bad stuff down here. So let's filter, particularly with volume. It's a lot easier if you filter so you don't have overlapping volumes. Okay, so here's, we can see now where all these problematic features are. And you can see they're kind of on the edges of the interface from the manifold down into the main volume. And it turns out that, and I didn't show these steps, but it turns out that when I fixed up the geometry, we ended up with a tiny little shelf surface here. And so you didn't really see that in any of the other cases, but what it does is it produces a ton of these really thin sheet-like tets at the edge because they have this tiny narrow base up here. And so, again, this lets you identify this. Okay, this mesh looks pretty good except for these. So all I would really need to do is go back in and redo that geometry to clean up this issue so that, there isn't this tiny little surface here. And that should remove this particular case here. Yeah, so that is sort of an example of setting up a complex 3D mesh like this. So now I'm going to go ahead and won't go back into the slideshow, but I guess I will. I'll go back into the slideshow and show here's what a simulation in that mesh configuration would look like. So on the right-hand side, you have the magnetic field. Boundary conditions for the magnetic field are oscillating at a pretty high frequency in the tens of kilohertz up here on the manifold structure. And they're then injecting plasma down into this main volume. You can see this is building up a magnetic structure in there, as well as heating the plasma throughout the volume, but primarily in this main volume. So this shows you, once you generate a grid like this with Cubit, it does, of course, work for simulation. Okay, so now I'm going to go through building a hexahedral mesh for also 3D nonlinear MHD. But this is going to be a multi-region mesh where we want to have multi-physics. So we're going to have plasma physics in some regions, a plasma model in some regions, and then just a conducting structure model in the other regions. So in this case, it might be a little hard to see, but there's sort of a pink toroidal structure. That's where the plasma is going to exist. And then we want to see how that interacts with these gray conducting plates that are very close to the plasma. All right, so hopping back over to Cubit. In this case, I'm going to kind of run through this with just the journal file. So hopefully you can see this on the side. I know oftentimes it is a little small, but hopefully you can give a sense. So you'll see here, I'm going to work my way through, and just the nice thing about journal files is you can select a group and then just play that group. You'll see this first section here. I'm actually defining things in terms of APRIPRO variables so that in the future, if I wanted to adjust any of these things, move the position of the wall, I can do that, and I don't have to actually change any of the geometry construction. I just have to change the variables at the start. And I'm going to build this up, geometry up fully in Cubit instead of importing from CAD. So basically the way I'm going to do this is, because this is a very toroidal structure, if you noticed from the CAD, I'm going to build everything up basically in one plane and then revolve things around. So first I'm going to build the top of one of the shells here. And then using that, I'm going to define a plasma cross section inside, which you can see can come up along the shell a little bit. And then you notice as I build, there's a scaffolding point. So I'm going to go ahead and delete the scaffolding point. And then I'm going to go ahead and start building up the 3D structure. So first, I'm going to go ahead and sweep the shell segment around here. You notice what I've done here is I've done two sweeps. So the first sweep corresponds to where the actual conducting shell is. And then the next sweep corresponds to the break between conducting shells. So each of these are going to have different physics models happening within the code once we export. Okay, so I've started this with the shell. Now I'm going to go ahead and sweep around the plasma model. So I'll go ahead and do that. So now I've created this full toroidal plasma, but this is just sort of the top. So I'm going to reflect everything in Z. And then I'm going to do some unites in order to clean up the structure a little bit. So now you can see, okay, we have this toroidal plasma and placeholders for where the conducting shell is going to be and where the breaks are going to be. All right, so put in a little bit more detail. So actually the shells top and bottom are slightly separate. So I'm going to put in breaks at the mid plane on the shell. And I'm going to do this by using web cuts, a centimeter above and below the mid plane. And then I'm going to go ahead and take this structure and clone it, just repeating it around the torus. So all it is repeating this 9 times around the structure. And I do that by doing a rotation. Okay, so now I have this whole structure built up with the shells, the alternating breaks, and the plasma region. And now the last thing I need to do is create essentially the outer volume inside of the main chamber. So all this sits inside of a larger chamber. So I'm going to go ahead and create that. All right, and now I'll make things transparent. Okay, so all right, so now I have all these regions. I need to make the geometry compatible going forward with Cubit. And so basically I need to make cuts in this larger volume of all of the other components so that then I can imprint and make sure that all the geometries match. So going to do these through chops. So first I chop the plasma volume out of the outer structure. And then I have to chop all of these shell segments, which would in general be a pain. But again, you can do this functionally with a loop. So I'm doing this in EpriPro, but you could do this, of course, similarly in Python with relevant commands. So now I'm going to go through and you'll see a bunch of flashes. It's just going to chop out each of these shell components. So you go through. All right, and then I'm going to go ahead and create a cut across here because what I want to do is basically generate the mesh in the same way that I just generated the geometry. So I want to create a cut so that I can, generate the mesh on that cut and then revolve the mesh in the same way that I've generated the geometry in the first place. So first I have to do an imprint and merge. All right, so that cleans everything up. And then I'm going to define blocks at this point before I generate before I generate the mesh. And the blocks in this case are what we're going to use in the code to identify the different regions where we have different physics going on. So I'm going to define essentially, 4 blocks here, one corresponding to the plasma, one corresponding to the shells, one corresponding to the breaks between the shells, both at the midplane and in between, and then one corresponding to that region outside the shells and the plasma. So we'll go ahead and define those. And then if I go ahead and look under the tree here for blocks, I can see the individual blocks. So that's the plasma. This is the shells. You can see every other segment missing the midplane. This is the breaks in the shells. And then this is the outer volume. And so again, this flexibility that we can then output through Exodus to generate our models. Okay, so now I'm going to just remove some components here so that we can see what's going on. Actually, let me just do this. Okay, so now I'm going to start making the mesh on the surface. So let me go ahead. I'm going to start out by making the mesh on the plasma. And then I just want to look at the mesh. So I'm just going to go here and say draw face all. And maybe I didn't actually make the mesh yet. Oh, yeah, I didn't make the mesh. All right, so now I draw face all. All right, and so now we can see this cross section that I'm building up. So this is the mesh in the plasma. In this case, I'm just using a pave for simplicity. Then I'm going to go ahead and make the meshes for the shell. And similarly, if I do draw face all, I can see this as it's getting built up. So we can see now we have a mesh on the cross section of the plasma, mesh through the shells, and mesh through the outer region. And of course, I can make this finer if I wanted to. All right, so now I'm going to go ahead and go back to the volumetric view, which I can do by draw volume all. All right, make this transparent so we can see things going through. You can see I have this mesh here on my one plane. And now what I'm going to do is sweep this around. So I'm going to sweep around the shells on half the torus. And then I'll sweep the plasma on that half the torus. And then I'll sweep on the other half. Okay. And now I have a nice swept grid. And in this case, you can see it looks a little bit chunky, but what I can use is a higher order mesh export. So I can use like a hex 27 type to provide curved elements in this case, which will allow us to better capture the geometry. And you can see by providing this sort of swept structure, the mesh is more or less matching sort of the direction of the geometry and also the direction of the underlying plasma structure. Okay, and so similarly, if we go back and take a look at this, here's examples of simulations in this code, or this mesh I'll show case on the left. So this is showing plasma temperature in the interior and current driven in the conducting structure. in the red and blue color bar here in the shell. So you can see as this plasma instability develops, we get currents that try and screen out magnetic field, which is trying to get pushed through the wall. You can see this here in a cross section here. This is the magnetic field, and the currents as the shading. As it tries to move through the wall's pushing back and keeping the field in the volume. And here's sort of what it looks like in 3D. All right. So I think I'm getting toward the end of time here. I'm going to try and run through this really quick, but if people have questions or if there's questions in the chat, feel free to drop those and I can stop and just answer them too. Okay, so last one is building a triangular surface mesh for 3D eddy current models. So all of these devices, essentially you have a core chamber, and then you have these magnetic systems. In between those two, you have a large structural component, which is called the vacuum vessel. So there's not actually a vacuum necessarily inside in future devices, but there's relatively low pressure at the edge of the plasma compared to atmospheric pressure. So you have this large pressure vessel that has to exist, which generally means a large amount of conducting structure in between. So what you want to do is understand how the magnetic systems will interact with this large conducting structure. And these conducting structures are in general 3D. So basically this sits outside of, this is a cutaway of a full experimental design. This is the eater one, and you see there's a bunch of ports coming through this vacuum vessel structure. So it provides a lot of 3D character that we want to be able to capture. Okay, so similarly, we can do this in Cubit. Again, I'm going to go ahead and use a journal file in this case to run through. So the first thing we're going to do to make sort of an example case is we're going to go ahead and create just a simple torus here. So we've just created a torus volume. The first steps I'm going to go through are basically like creating something like what we might get from a machine when we actually start to do one of these models from one of their engineering groups. So this is just a total torus, but what I want is a torus with some ports in it, so it looks something like what I showed on the previous slide. So I'm going to go ahead and make some ports by just making a brick, cloning it around the torus, and then using that to make cutouts. So here I made my cutting tool. I will go ahead and now cut the ports out. And then, so oftentimes we get something like this, where, what it is it's volume model. And what we want to do is convert that to a sheet model. So there's several ways to do this in Cubit, but what's often very convenient for us to do is to basically just copy the surface off of one side of the volume and then use that as our mesh. So in this case, I'm just going to go ahead and go in and make a new surface by copy and transform. And I'm just not transforming it. And I'm just going to select this surface on the outside. Okay, so now I've made a copy of that. And then what I can do is just go in and delete the original volume. So I go ahead and go in here and just delete that volume. And now I just have the surface, which is ideal for the type of modeling we want to do. Okay, so now similar to before, what I'm going to do is make some cuts in this model because I need to also define effectively jumps in multi-value potentials. So I'm going to make a toroidal and a poloidal cut. So a cut at the midplane here. So this gives me now curves that go the short way around the torus and the long way around the torus, which I can use to define those jumps. But it turns out that this model, basically what you need to do is define a jump for every topologically distinct path. And essentially you'll get topologically distinct paths for each hole you have, hole in a topological sense, in the geometry. So in this case, a torus actually has 2 holes. So that's why I need these first 2. But then I've also punched a bunch of other holes in it. So I also need to identify that I need to introduce jumps for each of these components. And again, I can do this straightforwardly. So first I'll do my imprint processes. And then I'm going to go ahead and define a block in this case. In this case, I'll just say I have 1, but I could do, for more complicated models, more blocks can allow us to set materials and things like that. And then what I'm going to do is I'm going to use node sets, the node set feature, to define all of these basically jumps that I'm going to have in my model. So I'm going to just go ahead and run this because I'm running out of time instead of doing it in the GUI. So I'm just going to sort of ahead and play this and then show you the result. So what I've done here is I've defined 11 node sets. And if I select all the node sets, you'll see they correspond to one vertex on each of the ports, except for you'll see I'm missing one. Don't worry about why that's true. It turns out you need all the holes minus one. This is a detail that's beyond the scope of this, but you can see basically I've pointed out to the code that each of these holes corresponds to something that needs a jump associated with it. And then I've also identified these two other holes that otherwise you wouldn't know. They're not on the boundary of the mesh, they're on the interior, but I've defined these two loops. So I've defined all of the topology that the code needs to then construct these jumps. So I go ahead and then can just make the surface mesh. And so you see before, by defining the node sets based on all of the actual geometric entities, now if I go back and I look at my node sets, you see it's going to save out within the Exodus file all the points that sit on these particular locations. So I just identified a vertex on each of the actual portholes. So there's just one for each of those, but you can see for each of these ones that correspond to a curve, it's now going to output this list of points that form this loop. And then I can use that within the code to properly identify where to place these jump elements within the model. Okay. And I'll just kind of show, again, pretty picture. So, okay, so here's a movie of something where this might look like. This might be hard to see, but this is a complex vacuum vessel model where we're basically rotating a helical current structure around internally. And this is something that actually might happen due to plasma dynamics, and you end up getting this sort of barber pole-like rotating current structure in the vacuum vessel, which can generate forces and corrupt diagnostic signals, things like that. So it's important to understand what's happening here. Okay, so yeah, I think I'll just leave this summary up here so I have time for any questions. But yes, main summary is, there's this need in the fusion industry. We're exploring this with our toolkit, and Cubit is providing a really powerful and flexible tool for us to, explore these modalities and figure out, the best way to interface and the best way to produce these tools to support commercial development of fusion. So thank you very much.
Thank you, Chris. That was a great presentation. We also have an open question about dynamic meshes and adaptive mesh refinement.
Yeah, so none of the codes we have at the moment use adaptive mesh refinement. We did previously interface with one of the capabilities within the code to do, well, I guess there's two things. So we don't do adaptive mesh refinement. We do have functionality in the code to do static refinement of the grid to build a multi-grid mesh, which we use for some of our solvers. So in that case, as we're refining the surface of the mesh, we use information. In general, what we use is we use information from the higher order elements, if that's present, to basically retain the curvature that existed in the initial elements. We also do have interfacing capability for a component that we haven't used in a while, but I believe is still there, called refine parallel. And this saved out information for the CAD in a format that can be loaded in by a library called OpenNURBS. And then you can use that to actually place nodes exactly on the correct location on the boundary, for kind of arbitrary precision. But that's the extent of what we've done, as opposed to dynamic or adaptive mesh refinement.